We will start at 4 o'clock. I will just share the slides. Are you able to see the slides?
Yes, ma'am.
Okay. So, good evening. Welcome to week 4 assignments of the NPTEL PMRF tutorials of the course Introductory Organic Chemistry II by Professor Harina Chakrapani and Professor Neeraja Deshaputre. Myself, Anisha Suresh, PMRF TF for this course from IIT Bombay. So, coming to the week 4 summary of the modules, in week 4, ma'am have discussed regarding the carboxylic acid and its derivatives and reactions of carboxylic acid and its derivatives, followed by a brief discussion regarding the alcohols, ethers, and epoxides. And a special topic was also discussed in this week, that is the 1CB reaction. So, coming to carboxylic acid and its derivatives. So, this is the structure of carboxylic acid. And when this OH is replaced by other groups which are represented by X, it will be carboxylic acid derivatives. So coming to the different carboxylic acid derivatives, so when the X is chloride, they are known as acid chlorides or either acyl chlorides. We use the terms interchangeably. And when this double bond OR group is coming, O double bond OR group is coming, it is known as acid anhydrates. And when OR group is coming, it is esters. And when NH2 is coming instead of X, they are known as amides. So we have discussed regarding the reactivity of each of this carboxylic acid derivatives and all. So how substitution reaction is taking place in carboxylic acids. So we have seen. So this is the trigonal planar geometry of our carboxylic acid or carboxylic acid derivatives. So it go through a tetrahedral intermediate and then we will get a trigonal planar product. So we are having the carboxylic acid or carboxylic acid derivative in the presence of a nucleophile. The nucleophile will add on to the carbonyl and this C double bond O will break giving O minus. So we will result in a tetrahedral intermediate. And once the O minus is coming back, thus X will be a group which is having better leaving group ability. So that group will be eliminating, giving a trigonal planar product with our nucleophile in place of X. So this reaction mechanism was confirmed by means of this O18 labeled carboxylic acid. So in the presence of water, this is what is taking place. X will be replaced by OH. And there can be a migration between, rapid migration between, like when this OH is going like this, we will get a migration of this O18 between these two oxygen atoms. So the mechanism is the water will be adding onto this electrophilic center of this carbonyl, and this C double bond O will break, leading to formation of this O minus. And now there can be a rapid migration of protons between this two oxygens, leading to formation of this tetrahedral intermediate. Now, having this tetrahedral intermediate in hand, this O minus can fall here, and the X, which is a better leaving group, can eliminate, leading to formation of this product, which upon deprotonation will give this. Here also O18 will be there. Okay, give this final carboxylic acid. Now. Uh, there is a chance that this is OH2 plus, water is a better leaving group. So when this O minus is falling back, this OH2 plus can also eliminate. So it can result in the formation of this starting material back. That is unlabeled starting material we can get back. Now coming to reactions of carboxylic acid and its derivatives. For the reaction to take place, there are different conditions. So this is the reaction. X is getting replaced by Y minus. This is the nucleophilic addition reaction that we have seen. So X must be a better leaving group than Y. So this X, in order to get removed, it should be a better leaving group than Y. Otherwise, we will get the starting material back. Then Y must be strong enough nucleophile to attack RCOX. So there should be a good nucleophile so as to attack at this electrophilic center of the carbonyl. And RCOX, it should be good enough electrophile to react with Y minus. So it should be a good electrophile and it should be a good nucleophile, as well as X should be a better leaving group. These are the conditions for this reaction to take place. And the reactivity of different carboxylic acid derivatives is as shown below. Acid chlorides or acyl chlorides will be more reactive compared to acid anhydrides, compared to esters, compared to amides. Amides are the least reactive among the carboxylic acid derivatives. Okay. Now coming to the different reactions that can take place for the carboxylic acid derivatives. So this acid chlorides can be easily converted into this acid anhydrates, esters, amides, etc. Similarly, anhydrates could be converted easily into this esters, amides, etc. And esters could be easily converted into this amides. Then amides, in the presence of strong acid or base, it could be converted into carboxylic acid. And carboxylic acid, by treatment with different reagents like SOCl2, PCl5, oxalyl chloride, etc., it could be converted into um, hello, someone unmuted. It could be converted into acid chlorides. So these are the interconversions between different carboxylic acid derivatives and carboxylic acids. Okay. Then in alcohols, ethers, and epoxides, these are majorly discussed in Introductory Organic Chemistry Part 1. So here, ma'am have discussed a very minor. So the major reaction that is discussed in this part is the Williamson ether synthesis. So here, in the presence of sodium metal, this alkoxide ion will be formed, and this alkoxide ion will undergo an SN2 type of reaction with alkyl halide, leading to removal of X minus, and an ether will be forming. So this is the mechanism of Williamson ether synthesis. And in finally, E1CB mechanism reaction was discussed, where this sort of a system having an X, which is a better leaving group, uh, this base will be abstracting the proton that is adjacent to a carbonyl, and an enolate will be forming. And the enolate, once it is falling back, this double bond will shift to this position, and this X, which is a better leaving group, it will be eliminated. It will lead to formation of alpha beta unsaturated carbonyl compounds. So this first step, where the formation of enolate is taking place, it is a fast step and it is reversible. Like it can lead to formation of the starting material back. And this stabilized anionic intermediate, it will be converting into this alpha beta unsaturated ketone. This is a slow step and it is a rate determining step, giving this alpha beta unsaturated ester. So this mechanism is known as E1CB elimination, elimination through conjugate base. So for going through this, for further references, you can follow Claydon Organic Chemistry Chapter 12 and Chapter 19. Now coming to the questions from assignments of previous year. So this is the first question. Acetyl chloride can't be obtained by treating acetic acid, that is CH3COOH, with APCl5, BCHCl3, SOCl2, DPCl3. Which is the right option? Yes. CHCl3 will not react with acetic anhydride to give acetyl chloride. We have seen that thionyl chloride PCl3 or PCl5, it can react with um, acetic acid to give acid chloride. Okay. This is clear, right? So the right answer is option B, that is CHCl3. Now coming to question number 2. So here this alcohol and this alkyl halide is there, and it is treated with NaOH in ethanol condition and heated. So we will be getting some major product along with byproducts like NaBr and water. So what is the major product that will be obtained here? Yeah, option A will be the right answer. So we can see the mechanism. So NaOH, so the OH minus will be acting as a base. It will abstract the proton and this O minus will be forming. That O minus can attack this alkyl halide sort of S, SN2 mechanism. So this Br will be leaving and it will lead to formation of this ether. Is the mechanism clear? Okay. So the right option is option A. Now coming to question number 3. A chemist carried out a Fischer esterification using methanol that was isotopically labeled with O18. So this asterisk is indicated that this is O18 oxygen. Identify the product after the reaction. What will be the product that we will get? B. Yeah, B will be the right answer. So we will see the mechanism. So here in Fischer esterification, this alcohol ketone will be protonated, and this methanol will add on to this carbonyl carbon, and this bond will break and OH will be forming. So we will get this intermediate. Now uh, like proton transfer will take place from this methanol to alcohol, means OH, and OH2 will be forming. So once this will be falling back, this water will be getting removed and we will get this product, which upon deprotonation we will get this major product. Clear? So as you told, this will be the major product that we will be obtaining. Now coming to the question number 4. Which of the following acids has the smallest dissociation constant? So we know acid dissociation constant is known as Ka, and we are aware of pKa. pKa, when it is decreasing, acid will be stronger acid. As Ka increases, acidity increases. So here they are asking for smallest dissociation constant. Which among these acids will be having smallest dissociation constant? C. C will be the right answer. So we can see the acid dissociation constant, it is used to distinguish strong acids from the weak acids. So strong acids will be having exceptionally high Ka values. That is, as I have told, as Ka increases, acidity will increase. So the Ka value is found by looking at the equilibrium constant for the dissociation of the acid. Higher the Ka, the more the acid dissociates. So this is how Ka is. Ka equal to concentration of H plus into concentration of A minus divided by concentration of Ha. So for Ka to increase, this H plus A minus concentration should increase. So the more the acid is dissociating, the more will be the value of Ka. And if it is a good acid, if it is a good acid, it will means strong acid, it will be dissociating at a faster rate, so we will be getting higher Ka value. Okay, so among this, if we are comparing the acidity here, Br CH2 CH2 COOH. So this COOH, the conjugate base, that is COO minus, should be stabilized. So this Br, it is a electron negative. Br is a electronegative atom, so it will be inductively withdrawing the electrons. But since it is one atom away, the effect will be lesser. When we consider fluorine, fluorine will be having greater electronegativity than that of bromine. Because of that, the fluorine will be withdrawing this negative charge at a greater rate compared to that of bromine, and it will be stabilizing the negative charge of COO minus. Hence, this will be good acid than when bromine is present. So here, when bromine is present adjacent to that of the COOH, its effect will be much more compared to when bromine is present two atom, like one atom away. Okay, that is why this is having the smallest dissociation constant. That is, Ka value is less for this compound compared to others. So now, when I am asking you to arrange this in the order of acidity, what will be the order of acidity? Which will be stronger acid? If I will number this like A, B, C, and D. Hey, Rara. Hey. Hello. Which will be stronger acid? Stronger acid will be A. Which will be the next stronger? Yeah. Since fluorine is present, it could be, but bromine is adjacent here, na? So it should be much more acidic, because the inductive effect will be more pronounced when the electron withdrawing atom is next to the group. So I think it will be this D1 followed by B and then C. So the least acidic compound is compound C. So it is having the smallest dissociation constant. Clear? Any doubts?
ఎప్పుడైనా పెళ్లి సంబంధం వెళ్తే అయిపోదు ఆ ఫౌండేషన్ చాలు
Hello.
రమ్మంటారు బయట లేరు బాబు చూస్తున్నారు ఒప్పుకోరు టైం అయిపోలేదు ఇప్పుడు అటువంటి కాదు
Hello. Any doubts? Now coming to the next question. The formation. Hello. Anyone having any doubt in last question?
చాలు అటెండెన్స్ పడి
Hello.
మేడం అప్రిషియేట్ చేస్తా బయటపడి
You are not audible, Suri. Any doubts? So coming to the next question. The formation of cyanohydrin from a ketone is an example of. The formation of cyanohydrin from a ketone is an example of option A, electrophilic addition, option B, nucleophilic addition, option C, nucleophilic substitution, and option D, electrophilic substitution. Option B, nucleophilic addition is the right answer. So we are having a ketone RR dash, and when Cn minus, when Cn minus will which is a nucleophile, it will add on to this electrophilic carbon center. We will be getting this Cn, which upon protonation we will get this cyanohydrine. So this compound is known as cyanohydrine. So this is an example of nucleophilic addition. Clear, right? Now coming to the next question. By reacting with Grignard's reagent, other aldehydes than formaldehyde produce additional addition products, not additional products, addition products that include option A, tertiary alcohols, option B, secondary alcohols, option C, primary alcohol, and option D, carboxylic acid. Option B, secondary alcohols is the right answer. So when we are having formaldehyde, which is this, so the Grignard reagent, that is RMgBr. So this is having delta plus, this is having delta negative. So this will add on to this, and we will get R OMgBr H, which upon hydrolysis it will give R OH H, which is a primary alcohol. That is the case of formaldehyde. Okay, that is why they are asking other aldehydes than formaldehyde. So if we are having other aldehydes, that is some R group instead of hydrogen. So this RMgBr, this is having delta negative, this is having delta positive. So this will add. This will act as a nucleophile. It will add on to the carbonyl carbon, and we will get this tetrahedral intermediate, which upon hydrolysis we will get this secondary alcohol. Okay, this is secondary alcohol. Fine.
Hello. Hello.
Hello.
Hello.
Any doubts?
No, madam.
Okay. Then please unmute. So, in case if we are having ketone and it is reacting with this Grignard reagent, what sort of alcohol we will be getting? Instead of this aldehyde, if we are having a ketone and it is reacting with Grignard reagent, what sort of alcohol we will be getting? Is it primary alcohol, secondary alcohol, or tertiary alcohol? Yeah, we will be getting tertiary alcohol. We can see, like, we are having a ketone and it is reacting with RMgBr, we will get this intermediate, which upon hydrolysis we will get ROH. So this is a tertiary alcohol. So this is clear, right? By reacting the Grignard's reagent, other aldehydes than formaldehyde produce addition products that include secondary alcohols. Now coming to question number 7. So we are having a Grignard reagent and it is reacting with carbon dioxide in the presence of dry ether. So we will get a compound X, and that upon hydrolysis we will get Y plus MgOHBr. So what is X and what is Y? A. A is the right answer. So we can see the mechanism. So CH3MgBr, it is a it will act as a nucleophile. It will add on to this carbon of this CO2, and we will get this intermediate which is X. And this upon hydrolysis we will get this carboxylic acid, that is Y, and this will be removed as MgOHBr. So it is reacting with H3O plus under hydrolysis condition. Clear, right? Okay. So here the right answer is option A. Now coming to question number 8. Predict the final product in the given reaction. So we are having benzoic acid and it is treated with AgOH, silver hydroxide, and this allyl bromide. So we will be getting a product P. What is P? What will be P? Okay, we will see. So we are having this acid and the acidic proton here is this proton that is present on the acid. So AgOH, it will be having OH minus. It will abstract this proton and we will get this carboxylate, and this carboxylate can attack on this allyl bromide in this fashion, leaving Br minus, which is a better leaving group, and we will get this ester. Clear? AgOH. So this OH minus will be acting as a base. It will abstract the acidic proton of this benzoic acid. We will get this carboxylate, and that O minus will be attacking on this allyl bromide, and this Br minus, which is a better leaving group, will eliminate and we will get this product. Clear? Okay. So here the right answer is option C. Now coming to the next question. An ether is more volatile than an alcohol, having the same molecular formula. This is due to option A, dipolar character of ethers, option B, alcohols having resonance structures, option C, intermolecular hydrogen bonding in ethers, option D, intermolecular hydrogen bonding in alcohols. So ethers are very volatile and alcohols are not that much compared to ethers. So what is the right answer? As you told, intermolecular hydrogen bonding in alcohols is the reason. So intermolecular hydrogen bondings will hold the alcohols in such a way like this, OH. Like this it will be holding. So here the volatility of this alcohols will be less compared to that of ethers. In case of ethers will be in this fashion. So there is no chance for hydrogen bonding to take place in the case of ethers. Therefore, ethers can evaporate at a much faster rate than the alcohols. So the right option will be the intermolecular hydrogen bonding in alcohols is the reason why ethers is more volatile than alcohols. Clear? Okay. Now coming to the next question. The major organic product Q formed in the reaction given below is. So what will be the major product that we will be getting here? That is, they are asking only for Q. So this acetone is treated with diazomethane. We will be getting P, and it upon treating with ethanol in presence of sulfuric acid, we are getting Q. So what is Q? B. Let us see. So this is the mechanism. So diazomethane is in this. It is a neutral compound, but it is having a CH2 minus and N2 plus in that. So this CH2 minus of this diazomethane will attack on this electrophilic carbonyl carbon of this acetone, and we will get this tetrahedral intermediate. Now this O minus can attack at this position, and this N2, which is a better leaving group, will get removed. So N2 will remove, and we will get this epoxide. So this will be the P in our question. Okay. Then in the presence of the sulfuric acid and ethanol, this sulfuric acid will protonate this oxygen, and we will get this intermediate, and this ethanol will attack at this position, and this will open, leading to formation of this compound. Clear? So as you told, option B is the right answer. You can see CH3, CH3, OET, and CH2OH. Is the mechanism clear? Diazomethane, the CH2 minus of diazomethane will attack on this electrophilic center of this carbonyl carbon. We will get a tetrahedral intermediate, and this O minus will attack in this fashion, SN2 sort of fashion, and this N2 minus will be leaving. We will get this epoxide, and in the presence of this ethanol and H2SO4, this oxygen will get protonated, and this ethanol will attack on this carbon, and this bond will break, leading to neutralization of this OH, and we will get this product. Is this clear? Hello? Is the mechanism clear? Okay. Now coming to question number 11. The relative reactivity of acyl compounds towards nucleophilic substitution are in the order of. So here different carboxylic acid derivatives are given, and their reactivity towards nucleophilic substitution. So we have to write the order of that. So we have acid chloride, ester, amides and acid anhydride. Among this, what is the right order for nucleophilic substitution reaction? Option C, yeah. As we have seen when we were discussing the summary, the reactivity order will be acid chloride, more reactive than acid anhydride, more reactive than ester, and more reactive than amide. Acid chloride will be the most reactive, and amide will be the least reactive. So the right option is option C. This is clear, right? Reason if you tell when we are writing R double bond O Cl and R double bond O NH2. Here both are having chlorine and nitrogen are having electron negativity similar. So electron withdrawing ability when we are considering that will be almost similar. Then when we consider this resonance, since chlorine and oxygen are in means chlorine carbon are in different group different periods okay periods uh, since chlorine and carbon are in different periods, so overlap will be not that much great compared to that of carbon and nitrogen. So here resonance effect will be more pronounced compared to acid chloride. So here since resonance is pronounced, this electrophilicity of this carbonyl carbon will be lost. But in this case, electrophilicity will be as such. So acid chloride will be uh, more electrophilic compared to that of amide. Clear? Okay. Now coming to question number 12. Predict the products of the following reaction. So this anhydride compound is treated with ethanol and heated. So what will be the product that we will get? D. Option D. So we will see the mechanism. So we are having the anhydrate. Ethanol will add on to one of the carbonyl carbons and we will get this tetrahedral intermediate. Then a proton transfer can take place from this ethanol to uh, this oxygen. So then when this O minus will fall back, this bond will break and we will get a carboxylic acid here and an ester here. Then this upon deprotonation, we will get this compound. Okay, this is proton transfer. Then here deprotonation will take place. Is this clear? Why? Just again, this is anhydrate. Here we are having a carbonyl carbon and this ethanol will add on to one of this carbonyl carbon. Here two carbonyl carbons are there which are identical, so ethanol will add on to one of the carbonyl carbon and we will get this tetrahedral intermediate. Then a proton transfer can take place from this ethanol to this oxygen. Then once this O minus will fall back, this bond will break and we will get a carboxylic acid here. And this upon deprotonation, we will get the final compound, which is a major product. Clear? Okay. So the answer is option D. Now coming to the 13th question. So in which case would a Williamson ether synthesis will fail? So we are having sodium methoxide as the intermediate, and it is treated with iodomethane, iodoethane, 2-iodopropane and 2-iodo-2-methyl propane. So in which of this case Williamson ether synthesis will fail? Yeah. What could be the reason? This is 2-methyl 2-iodopropane. So this is a tertiary carbon, and here SN2 sort of attack will not be preferred. Steric hindrance will be there. Because of that, Williamson ether synthesis will fail in this case. Okay. So we can see the mechanism of Williamson ether synthesis. So they have given the sodium alkoxide. The first step is already given. We are having sodium methoxide in hand. So now we should have an alkyl halide, and this alkoxide will attack in an SN2 fashion, leaving this X minus, which is the halide, and we will get the ether. So for this reaction, that is the attack on this alkyl halide to take place, it should be preferably primary or secondary, because tertiary will cause steric hindrance for SN2 reaction to take place. So that is why this reaction will be failing. Clear? Okay. Now coming to 14th question. Among the following esters, the one that undergo acid catalyzed hydrolysis fastest is. So the ester to acid, that reaction which will be undergoing fastest. Option B. That is the right answer. The reason is that this OH, because of its electron withdrawing nature, it will make this carbonyl carbon more electrophilic. So the OH minus can attack on that at a faster rate. Means water can attack on it at a faster rate, and hence we will get the acid at a faster rate compared to others. Here the OHs at the meta position compared to at the ortho position. At the ortho position, it will be nearest to that of the carbonyl carbon, and it can have more influence on the carbonyl carbon. But here it is at the meta position, so this will be having less influence. And here the CH3 is an electron donating group, so it will make the carbonyl carbon less electrophilic. Okay. So this we have seen this is the mechanism for acid catalyzed hydrolysis. So first, in the presence of H3O plus, it will get protonated, and then water will add on to this. We will get this tetrahedral intermediate. Then one of the proton will be abstracted from this H2O plus, and we will get this intermediate, and this OR plus can abstract the proton from H3O plus, and it will give this tetrahedral intermediate. And this OH, upon falling back, this alcohol will remove, and this upon deprotonation we will get the carboxylic acid. So all these steps are reversible. It can give back the ester. That is why this double headed arrow is given. Reversible arrow is given. Okay. And the factors that determine the rate of hydrolysis reaction is the electrophilicity of the carbon atom and the nature of the leaving group. As we have seen, the nature of the living group, the electrophilicity of the carbon atom, the nucleophilicity of the nucleophile, these all factors will affect the hydrolysis reaction. Okay. So this is the right answer. Is this clear? OH will act as electron withdrawing group. Here the inductive effect we are considering into. Okay. Now coming to the last question of today's session. Match the reagents in list A with reagents in the list B, and we have given four options, out of which what is the right match. So anhydrous AlCl3 is given, reagents are given, and the reaction is also given. We have to match it. Anhydrous AlCl3, sodium and ethanol, metallic silver, potassium thalamide. So we are telling option C, it will be the right answer. So from first option itself it is clear. Anhydrous AlCl3, Friedel-Crafts reaction. So this is the right match, and none of the other options are having one as match to R. So we can confirm from this only, and we can see what are the reagents that are used in other reactions. So this is a Friedel-Crafts reaction, as we have seen in the first week. So benzene, upon reacting with AlCl3 and alkyl halide, it will give alkylation followed by elimination of HCl, giving this product. So here the reagent is anhydrous AlCl3. Now coming to blank reaction, as we have seen in the lecture, here metallic sodium is involved. So this ester is getting converted into two alcohols in blank reaction. So the metallic sodium is involved in blank reaction. And now coming to Gabriel synthesis. So here thalamide is involved, and here deprotonation is the first step. So we will get this N minus, and it will add on to alkyl halide, which is a primary alkyl halide, and we will get this product. Okay. So this is the Gabriel synthesis, and coming to an I state homologation. So we are having an acid, it is treated with SOCl2, we will get the acyl chloride, and then it is treated with diazomethane. So we will get this intermediate. Now N2 elimination will take place, and we will get this carbene. It can undergo a Wolff sort of rearrangement, and it will give this ketene. And then upon addition of water, we will get this homologated product. One carbon extra will be coming. Okay. So as we can see here, anhydrous AlCl3 will come for Friedel-Crafts reaction. Sodium ethanol will come for Planck reaction. Metallic silver is coming for an I state reaction, and potassium thalamide for Gabriel reaction. So the option C will be the right answer. Is this clear? Okay. So thank you all. So today's session is over. So we can meet on next Sunday for week 5 assignment solving problems. Thank you.